Hello, thank you for watching this video. My name is Pepijn van Oort. I am from Wageningen University and Research Center in the Netherlands. I will be presenting the bioeconomic seaweed model for modeling Kappaphycus cultivation in Indonesia. I am presenting on behalf of my co-authors who are working at Wageningen in the Netherlands and at Hasanuddin University, Unhas, in Indonesia. The seaweed species we are talking about is Kappaphycus alversi, which is locally also called cotoni. It is an economically important seaweed in Indonesia. In this presentation, I will start with showing you some figures of the cultivation. Next, I will present what we call the bioeconomic seaweed model, which is a mathematical description of the cultivation system. We are currently running an experiment to estimate parameters of the model. I will briefly present the experiment. The seaweed is growing just below the sea surface, hanging on these floating lines, which are kept floating with plastic bottles. A typical seaweed farm will have between 200 and 1000 lines. Each day, the farmer harvests and replants a number of lines. A line is normally harvested after around 45 days. The seaweed is harvested in rafts or boats. The seaweed is dried on the beach. We estimate that the water content is 90% fresh out of sea, 35% after drying on the beach. We call this semi-dry because it has 35% water. In this example, you can see a fresh weight of 160 grams per plant corresponds with a semi-dry weight of 24 grams and an oven-dry weight of 16 grams. Clearly, the moisture content has a big impact on what we measure. It is important to be clear what weight is reported. After harvest, the seaweed is cleaned. In the left figure, you can see in the top left a bucket with seaweed and green slime. The ladies remove the green stuff, ending up with a pile of cleaned seaweed, which you can see in the bottom left. Then they take an empty line and start attaching parts of the seaweed to this new line, making it ready to be planted back into the sea. Here we see the same. In the left, empty lines. In the middle, a line with seaweed ready for being put back into the sea. Before bringing back to the sea, the bottles are again attached. The start weight of the replanted line here in the middle figure is important for production, as we will see in the following slides. As you can imagine, labor costs are particularly high for these harvesting and replanting operations. We will get back to this further on in the presentation when discussing the economics. This figure shows how we think of growth. It shows three growth curves for three different environments. The horizontal axis shows the days after planting. The vertical axis shows the seaweed fresh weight. We hypothesize that growth can be characterized by curves like these, where growth is first exponential, but then flattens off towards a maximum. Please remember this is just for illustration. We are still running an experiment to accurately estimate the parameters of these curves. The start weight and the distinction between gross and net yield is important. In the bottom green line, we see farmers' practice, where almost all of the harvest is sold. But this low start weight results in slow initial growth and a low yield. Our models suggest farmers would do better with the orange line. A medium start weight gives much stronger growth and a higher net yield. The blue line shows a too high start weight is also not good. So we are interested in knowing the optimum medium start weight, that is the orange line. At the moment, we still have little knowledge of the exact values of the growth curves. We are conducting an experiment to better characterize these curves. Calculating net annual production allows for comparing cultivation systems with different cycles, such as here for harvesting once every 15 days, 45 days, or 120 days. A short cycle of 15 days gives 24 small harvests in 1 year. A normal cycle of 45 days gives 8 medium harvests per year. An extremely long cycle of 120 days gives 3 large harvests per year. This example shows a 120-day cycle gives much lower production than a 15 or 45-day cycle. Net annual production is slightly higher for the 15-day cycle, but recall the high labor costs of harvesting and replanting. Economically, we might find highest profits for a longer cycle. We first calculate net annual production, as I showed in previous slide. We calculate gross income based on weight, carrageenan content, and price per kilograms of carrageenan. For production costs, a distinction is made between fixed costs and variable costs, which occur only at harvesting and replanting. If harvesting and replanting is expensive, then it becomes more profitable to have longer cycles. Here we show some preliminary results of net farmers' income. We ran the model 49 times, with 7 different start weights, which you can see in the lines, and with 7 different cycle lengths, which you can see in the columns. The darker the color green, the higher the profits. This example suggests farmers can have the highest income with a cycle of 90 days and a medium replanting weight of 0.1 kilograms fresh weight per square meter. We visited farmers in Sulawesi and asked them about their current practices. They all report 45-day cycles, but they don't know well what start weights they are using. Their answers to these questions differed quite a lot. At the time of these visits, we did not have a balance with us, so we could not measure ourselves. Economic data on variable and fixed costs are hard to obtain. You will understand that the results presented here are quite sensitive to our assumptions for the two types of production costs, the fixed costs and the variable costs. So please do not take this figure for the truth. We are still collecting data to more accurately estimate parameters. The take-home message is that, once validated, a model like BESeM can be used to optimize management. As we are speaking, an experiment is ongoing. The experiment is led by Professor Gunarto and Dr. Rukmi Nassari of UNAS Hassanuddin University. Normally experiments with Kappaphycus are only for a short period. Here, we are monitoring growth for 120 days. We are sampling in 6 locations at different distances from the river, hoping to find growth correlated with environment. From the data, we hope to find something like this: measured data from which we can estimate the growth curves, with side differences as determined by the environment. We will be able to estimate these curves when the experiment is completed. That will be at the end of this year. We like to end this presentation with a quote from a famous Wageningen professor: "No modeling without experimentation, no experimentation without modeling." This is also our philosophy. Models can help us understand reality and support farmers, but models need to be tested and developed through experimentation. And with this, I like to conclude my presentation. Thank you for listening. If you want to know more, please contact the persons listed in this slide. Once again, thank you for listening.